to everybody. And tonight we're going to talk about Coriolis meters. And I know that some of you guys know Coriolis meters very well. And I can see there's some new faces, so I will try and balance it, not to bore the very experienced people, but also not to lose the new people. Everybody's been exposed to Coriolis meters? Everybody more or less? Never heard of that? Okay, so it's from never heard of it to very experienced people. Alright, then I'll try and do my best. Just to run over the principle of the Coriolis meter, it's basically a tube. You can have a single tube or dual tube that's resonated or vibrated. Excited. And you need to think of the movement, not as shown as there, but similar to a tuning fork. So if you hit a tuning fork like that, you can hear it, but you can barely see the movement. So the movement is very, very small. Okay. And what then happens if you put a flow through it, this tube bends, and that is the Coriolis effect. I'll play a movie a little bit later to demonstrate that better, but that is the Coriolis effect. And what happens is the more it moves, the higher the mass flow. So this is the tube, yeah? This is the tube. That's the way it bends when excited. Okay, no flow through it. And as soon as you put a flow through it, it bends in this way. Okay, and this is out of phase. In other words, that's a sine wave, and this is out of phase. And the more it bends, the higher the mass flow. Then we also get the density from this measurement. How does that work? That is related to the frequency, the resonant frequency. In other words, we excite the tubes, and they very happily go like this at a certain frequency. Then if you put water into it, it goes slower. The frequency gets less. If you put honey through it, it's going even slower. So that's related. It's quite easy. And then of course we also take the temperature. Any idea why can we get temperature from a Coriolis meter? I know Johan asked me why can we not get pressure from it. But there's a very specific reason why we have to measure the temperature. And the temperature is not there just to have a temperature up, it's there for a specific reason, sorry?
It's there to cause certain densities change with temperature.
Compensate for
changes.
It's there to compensate for the temperature, okay, because you have an expansion coefficient. Yeah. And the tubes are, I have some tubes here. There's the tubes, there's the exciter coil, and here are the two pickup coils to pick it up from bending. And here's the temperature. Okay, there's the temperature. So we have to measure this because this is fixed between 2 points. And as the temperature goes up, and you guys sometimes use very high temperatures, this needs to go somewhere. Okay. Why do we get straight tubes and bent tubes? This is straight tube. Why don't we make all the tubes? Why don't we make them all straight? Why do we have some like this?
Due to temperatures and process conditions. Where does it go to if it expands?
That's it. That's absolutely that. Where does it go to? So this one can take much higher pressures, temperatures, because it can expand. This is limited. This material is titanium. Why? Because the expansion coefficient is a lot less than this. This is 904 stainless steel. So there's specific materials for specific reasons and specific shapes for specific reasons. So we measure that, and then because we measure the temperature, we can also give resonant output because it's measured very accurately. So that's a multivariable that we get from the Coriolis meter. That we spoke about, that is the density, the way it's resonated, and you can see here, for instance, with air, it resonates at a different frequency than to water.
Well, just a question, you're up to viscosity?
I'm getting to that.
Okay, no, I just don't want to jump the gun.
This is the very standard parameters that you can get from a Coriolis meter. I'll get into the more special stuff now. Can I play a movie on the Coriolis meter, which can describe it a lot better than what I can? Chase it up a bit.
Often display completely different properties. Consequently, there are different principles for their measurement. One such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly. Here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriolis measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously but independently via the tube oscillation. Andrus and Hauser has continuously revolutionized and perfected Coriolis flow measuring technology in numerous innovative systems. This measuring technology is unique, as it's the only way multiple process variables such as mass flow, volume flow, density, temperature, and even viscosity can be measured simultaneously in pipelines. For all applications, we have the right solution.
This is a little bit of marketing garbage at the end, and I was told that I must stick to technical stuff and no marketing, but I was already bashed with the opposition and this and so I'll try and stick to the technical stuff. But that's a good movie, that explains it quite well, don't you think? So we get lots of shapes. I've shown you a straight tube now, there's a straight tube. I've shown you a little bend tube. But this is all the shapes that you can get in Coriolis meters for various reasons. The only thing is that you really need to consider that when you want something that can drain. Lots of applications you want it to drain out. Okay. And then you need to have a careful look at the design of the tubes. We get very small Coriolises these days. This range here is from 1 to 6 millimeter, and they are busy currently manufacturing even smaller, 0.1, 0.2 of a millimeter. Very, very small. They can measure drops of a drop. Perfume, for instance, really needs to be measured. So that's on its way. It will be soon available. So very small to very big. And if I say very big, I'm not only talking about physical size, but the volume that you can put through it. So we're getting to very, very big Coriolis meters. They also manufacture them very compact. For loading carousels, you need to pack them very densely. And then, of course, there is for Mr. David, 2-wire Coriolis meter,
Loop powered.
4 to 20 milliamp loop powered.
Fantastic. Up to what size?
150 so far. Why? Why only 50?
It's the size of the tubes, the excitation voltage you need.
Exactly. To excite this, you need energy, and there's a limit on this. It's improving all the time. It will come. And yeah, to answer that, why? It's logical. All these instruments are 4 to 20. Most instruments are 4 to 20. That's the standard. So, and there's a big drive to make the Coriolis now as well. What also makes it a lot easier for you guys with hazardous areas is the installation. Now you can open the housing, where previously you can't because the housing is EXD. Okay, now you can open it, you can work with it, and I know that lots of your areas are hazardous areas. So 2-wire Coriolis makes sense.
Just a quick one while you're on that topic. The mag flows are still up to 8 inch.
Yeah.
Nice one confirm. Get my paradigm fixed again.
Also high pressures now coming available. So Coriolis has started off with 1 meter, and now you can see it's developing smaller, bigger, all these sort of requirements from the market. The developers are doing that now, so we can get very high pressures. And then there's a new one. I know that this sort of technology evenings is normally around, so what is new in the market? Okay, you guys want to know what's new. There's a 4-tube Coriolis meter now in the market. That's what it looks like. Why a 4-tube? Well, you know that you get pressure loss. That's one of the big problems for Coriolis meter, you get pressure loss. But if you have 4 tubes now, it's less. Your pressure loss is less. It's more compact, and you get very good tolerances. Why? Because it's in balance. If you have a single tube and you excite it, you need to have a counterweight. Okay. If you excite this thing, you need to have a counterweight, otherwise it vibrates. So if you look at this sort of the single tube construction, there's a counterweight. It's normally a pipe over it or something to counterweight it. That is one reason for having the dual tube, because the dual tube is vibrated like that, and that keeps the system in balance. Okay. But now they put another 2 on top. Okay. Then you're in balance in another plane. So the whole setup is a lot more stable and less influenced by vibration. And what they found is that the repeatability is very, very good. There's one installed. So repeatability is better, accuracy, compactness, and pressure loss. These are the main features. Then of course we can do viscosity with the Coriolis meter, and this becomes a little bit more specialized. And you can only do this with a straight tube. So over and above, over here, we excite it like that, in this direction, like that, and that gives us the mass flow and the density as we've seen. And then over and above it, and remember the movement is very small, like I said, a tuning fork, so it's very, very minute. And over and above that, this is fixed between 2 points. This is also twisted in this direction. And it's twisted at a different frequency. It's twisted at about 900 Hertz. And if you fill this now with water, you can twist it quite easily, 900 Hertz. But if you fill it with honey, it goes slower because it's more difficult. You need more energy to twist it. And that power required is measured, and that's related to the viscosity.
Also up to a certain size, currently?
80 millimeters, 3 inches. Viscosity up to about 4,000 kilograms per cubic meter. There's also a limitation on that. that's very, very thick. Here you can see, this is actually what's happening. This is what's measured, is how the fluid sort of sticks to the side of the tube. Alright, then concentration measurement. And I think this is maybe something new, but we can also do that. There's a Coriolis meter. This is in a distillery, and it's measuring alcohol. Can anybody guess how they do this? I have the price here. I can give the price. If everybody can tell me how they measure the concentration in that brandy that you poured at the back there, I think it's about 40% per volume. And that's measured and controlled by a Coriolis meter. Now,
It's also about mass or what?
by density.
Yeah, by density, mass flow, the density of the, because the alcohol is density is less than the water.
What they do is you have a carrier fluid, okay, and then a target fluid. Now this gets a little bit complicated to calculate this and to measure it, but I'll show you now how it's done. But it goes around the density measurement. It's the same with bricks. Now bricks is the measure of sugar in water. 1 degree bricks is 1 gram of sugar in 99 grams of water. Okay. That is something that you get in the food industry. That's a term that they get there. And of course no alcohol in this case.
The only way it would be possible is you'd have to pass a sample volume first, and then compare it to exactly the same volume and see the difference between the two, and then look at the percentage, the difference.
I'll show you now.
Yeah.
That is if you don't have
Yeah,
the
yeah,
information.
I think tasting it is much easier.
And cheaper.
We also measure the solid contents in sludge or effluent. You don't want to taste that.
No. But I suppose it's the same principle. You pass the sample and then pass the actual volume and see what's the difference between the two.
That's it.
And you
That's
see the
when
impurity.
you do this when you don't have the information.
Yeah.
Okay, and I'll show you now. So what happens is that, okay. So the standard meter, without this concentration measurement function, can measure density, and from the density we can also calculate volumetric flow. So we have mass flow, and that's a direct measurement. It's not a calculator, it's a direct measurement of mass flow. Then we have density measurement, which is also a direct measurement. Then we divide the mass by the density, and we get the volume flow. Now the volume flow is a calculated parameter now, okay. That we can get standard. Now with the concentration measurement, we can get degrees bricks, API, balm, and Plato. These are standard formulas in the Coriolis meter, pre-programmed. You can switch the thing on, you can put the water with the sugar through it, and you can select, I want degrees bricks, and it will give you the reading. Spot on. But if you now come and you say, I want percentage mass or percentage volume, that concentration measurement of the alcohol, that becomes a little bit more tricky. Now we have to do some calculations. How this is done, this is a table of a standard, it's a bricks table from, I think the body is in Kumsa. Kumsa is the food body that calculates this. So this table gives us on the one leg the temperature, and on the other leg the concentration. And this is the density. This is what we need to know. We need to know how the density changes with concentration related to temperature. If you don't have this, then we have to follow Uncle David's method of calculating or measuring it.
I always choose a difficult one.
Yeah. 2 wires, I mean.
Yeah, okay.
So that is a standard thing, a standard table. If we have a table like that, so if you want to measure now the alcohol in whiskey, you need to bring a table like this. I know there are tables like this, but let's say you are smoking Mampoer. Mampoer is a little bit of a different. And you tell me, yeah, but I want to sell this, and I need to. I know Mampoer, you normally control it about 60%. So you want to measure this very accurately because you're going now into production. And say, okay, we need a table like this. Okay. If you can produce a table, we take it, we put it into a calculator. It calculates all the coefficients for us, and it comes out with a sheet like that. And here you can see your expected accuracy. You can say, okay, that's good or not good or whatever. You can also then fine-tune it later on by taking samples, taking it to a lab, analyze it, and make the adjustments on the meter. That's how you can do concentration measurement. And if you can't produce a table like that, then you need to follow the more manual option of either measuring samples and making a table like that and make the adjustments. You can also get special density calibration. Density is normally calibrated with air and water, 2 points, but you can get a special density calibration and you can have other fluids put through it that gives you a much more accurate. You can also have a special density calibration if you have an application on the plant and you say, oh, we really want to know very, very accurately what is the density of this fuel in this place. Then you give the range and it's calibrated at that range. Otherwise the density range is normally from 1 to 100, which is a very long, and if you want to operate in this range, it might not be linear there. So that can also be done. Talking about accuracy, I'll quickly talk about calibration, and I know that you guys know calibration a lot more better than me. And it's always a case of between the suppliers, the calibration is 1% or 0.5 or 0.1 or whatever, and it becomes a little bit of a theoretical thing. But in real life, this is a case where they offload fuel to a tank farm. Now when the ship parks there, they pay big money per hour because it's a ship that wants to go in there. So they want to offload as quickly as possible. Hence the reason for going big Coriolis meters. But you also need to measure it very accurately. Why? Well, a barrel of oil, let's take it at about $100 today. And if you offload 100,000 barrels per day, that's what they typically offload from a ship, and you can improve the accuracy by 0.1%, you can save $3.6 million a year. Now if I say to you, I have a big Coriolis meter, and the cost of it is R1 million, you say, please, have a heart attack. But if that is what you're talking about,
Peanuts.
it's peanuts. You pay it off in a week or two. So that's when accuracy matters. If it's a water pumping at your house, it's not such a big deal, but in some cases...
They're going to overcharge you in any case in this place.
Here's another application of a loading tank farm, and you can see all the places. And what's happening with Sasol charging us so much money for fuel, you can see that fuel is getting... You talk about the municipality overcharge.
That's why we're still in business.
No, commodities are getting so expensive. Sorry, Johan?
Sorry for the record, it's not Sasol that's charging us, it's the government.
No, I'm just pulling your leg. I mean, you pulled my leg, so...
If Sasol would have charged it would have been half price.
But the fact is that commodities are getting very, very expensive, and there's so many places where they're offloaded. I mean, I was at a guy in Victoria the other day with LPG, and they don't measure it properly. So they measure that with a weigh bridge. They talk about 20 tons, but then he's selling it, and then somewhere this doesn't tie up, and then he needs to measure now accurately, okay, because he's losing money. And you can see, yeah, you measure when you offload, then you measure when it goes to the rail or the truck or wherever. So many points that you have to measure. So we're actually in good business, the measuring business, or flow measuring business, and then to measure accurately is very important.
And being in the mass flow business is even better. You don't have to compensate for your temperatures and the pressures and all this kind of, you measure direct mass.
I had a discussion with Johan and I said to him that that's actually another very interesting topic that I can't cover tonight,
Yeah.
but maybe at another time, especially when you start talking gas.
All right.
You know, because then volume is a big issue.
Yeah.
Okay. And I don't know how far the whole fuel industry is volume or mass related, but I get the feeling that everything is turning towards mass because volume is such an headache.
Oh yeah, it's a nightmare.
You don't want to compensate all the time. Just to talk about calibration then, you take this instrument, you take it to a rig and you calibrate it on the rig. And then you need to have this rig also calibrated.
I was going to say, we calibrate the rig.
Yeah.
Calibration rig. That's
The same kind.
So, what we say is a calibration facility is accredited only when it fulfills the requirements of ISO 17025. If you read that, it tells you exactly what needs to happen, and it's very, very stringent, very difficult. And this facility also needs to be approved. In South Africa, it's SANAS, that they come out and they approve this rig. And once you have this accreditation, it doesn't mean it's the end of the world, because you need to still comply with ISO 9001, and it gets checked once a year. So it's very, very difficult to run a rig like that. And as far as I know, the only one is Eskom's. And Fairley is battling to keep his accreditation. So what we're saying is that when you buy an instrument and you get a piece of paper, and it says 0.00000, you just understand that it takes the errors of the meter plus the calibration facility. So the meter can never be more accurate than the calibration rig. Because the calibration rig has got an error plus that of the instrument, that's what you get in your certificate.
The gas flow calibration rigs.
In South Africa,
No, in the world.
in the world,
Imagine these. But I can't imagine what it looks like, how they actually do it.
I can show you.
Because the flow is easy, they just do it by weight, you know. How do they do the gas?
I can show you. I have pictures, not in this presentation, but I'll show you
Show
afterwards.
us, I'd like to see it.
I've been in the one in Denver, Colorado.
And
You know, it's a plezier.
the problem with that is that it's so expensive that, you know, to run a calibration rig as a business, you need to have lots of instruments. It doesn't make sense.
That's why it's so expensive to have an XR.
Absolutely.
It's tremendously expensive.
Applications, I just want to show you some applications of Coriolis meters. I know you people are exposed to the oil and gas, but it's also used other places in the world. This is typically the ship offloading, a place in Sweden where they wanted to offload the ship as fast as possible, and Coriolis meters was a limitation. They wanted it very accurate and very fast, and this is what they did. They put two Coriolis meters in parallel, and they achieved what they wanted there. This is quite a big project, but I'll just show you that. Typical tanker loading, I think you guys are more familiar with that. Refinery, custody transfer, you're also familiar with custody transfer because that is also becoming more and more relevant these days. This is a petrochemical terminal, also custody transfer. And this device, who knows what is this device?
Looks like a filter.
Or a deaerator.
Deaerator. Points. I think you qualify for the prize.
No, that's not my intent. No, I just look at
Thank
the.
you, sir.
Yeah, it's really enough.
A deaerator. Why a deaerator? Why a deaerator?
Get rid of bubbles.
Because you pay for that.
No,
dollar.
absolutely, get rid of bubbles.
Yeah, because otherwise it will influence your whole.
That's the law. It's the law. If
Because you don't want to pay for air.
If you have a custody transfer, you no bubbles. Is any of the opposition here? Is there nobody working for the opposition here?
No, hey, Brian.
Right. Nee.
Hy is nie oppositie nie.
Somebody asked me, I think it was the last presentation about air bubbles. What do we do with air bubbles? Okay, and they have some filtering system in there. But that's a little bit of a gimmick to electronically filter things out. That's there. It's not really. So the law says custody transfer, no air bubbles. Okay, this is CO2 measurement in the food industry when you put bubbles in your, there you want bubbles in your Coke or whatever. Solids concentration, yeah, we can measure the solids that we spoke about, they calculate, and this is becoming relevant nowadays in the water industry. All the effluent and stuff needs to be measured from government. They also want to know how much solids is getting into that. Marine fuel, diesels, crude oil. This again is in the brewery where they're measuring density. Crystal liquor, which is very abrasive. Viscosity, alcohol, chocolate, and you can see there's a heating jacket around it to keep the chocolate flowing. I'm not trying to say.
With the heating jacket, won't that affect your measurement with the tubes and things? I'm thinking of steam jacketing and those kind of things on liquid sulfur and so on.
Why?
Expansions. I suppose you compensate for that.
Compensate.
Okay.
Compensate.
No, I've never seen one with a jacket.
You don't? You have not?
Yeah,
Yeah, I can avoid.
You're talking about offloading ships, crude oil. I mean, you have to have temperature, you have to have something to prevent chokes or whatever in crude oil.
Well, that's it. That's exactly it. I know in Sasol there's a lot. I've sold
Steam
a lot.
jackets.
Steam jackets, yeah. As soon as the stuff wants to solidify and you have the whole pipe with steam jacket or heat tracing, then you get a jacket across that.
No, I've seen a lot of steam jackets, but not around the Coriolis.
No. Okay. It's an expensive device. Sometimes they just take the heat trace it or they take the tube and just wind it around the meter.
Yeah, but the danger with that is it's not installed by the factory and the compensation can become a problem. But while if it's installed by the manufacturer and you've got a proper steam jacket around it,
The
no
problem with
problem.
some of the products is that they solidify when they get cold.
Like liquid sulfur and
So then
things.
you have a
That's the
problem.
biggest problem.
And that's why one good reason is to install it in a vertical position
Yes.
so that it can drain. Slurry applications, I'm going to talk a little bit about it now because that's maybe, I think it's relevant, and that's why I spoke to Gerrit about that project they're working on. It's abrasion, but that's not really abrasion. We are entering sort of dangerous ground with the mines and slurries. I'll show you a little bit later. Density measurement, density, that's also very often asked. The guy comes and they say, we have this huge pipe and we want to know, we want to calculate the mass, okay. So I don't have such a Coriolis meter, but we can put such a mag meter in, but how do we measure the mass? Okay, nuclear. No, we don't want nuclear, that's too much of a trouble. That specifically happens in Africa, they don't want nuclear. And we say, okay, well, put it in a bypass like this, use a 1-inch Coriolis meter, it's a lot cheaper. Take the density and you can calculate then your mass flow. But there's one problem still with this one. What is that?
All the solids, all your dirt is going to go. Is it always at the bottom of the pipe?
No, it doesn't need to be.
Okay.
Well, okay.
You can turn it anyway.
Yeah.
You need some restriction in here.
Otherwise,
Otherwise everything will just go through here. You need to force something through the meter.
That's what's happening typically with your viscosity measurement. Viscosity, you do the same.
Yeah.
If you have a large pipe, you want
Yes,
to measure viscosity.
Exactly.
If it starts clogging up,
Yeah.
it just clogs up more and more. The moment it starts clogging,
Yeah.
it passes more through the line. And then it just, there's less going through, it clogs up more. Eventually it's just clogged.
Sometimes it helps to have a control valve there that you can,
Regulate it,
or not a control valve, but a valve that you can
A
change.
variable
The
restriction.
idea is to have the velocity through the meter the same as the velocity in the big pipe.
Yes.
Then you have a current reading. Aviation fuel.
Now, but at that stage, you don't know what's the velocity in the pipe. I mean, against what you're going to measure it.
Yeah.
And restricted.
You see, you're going to restrict it or whatever and so on, but on which measurement you're going to measure
Depends
against.
on your whole plant. If you have other indications
Yeah, I
somewhere.
know, say you've got a mat flow somewhere in front.
That's it. Well,
somewhere.
so much is going through. You can calculate it somewhere.
The only thing here is, okay, somewhere in that pipe, normally they'll put a mat flow.
Yeah.
And you want just the density from this,
Exactly.
without nuclear.
Exactly. Yeah. And then we can see what is the flow through the meter as well. Aviation fuel is also moving in this direction where they mount this on the trucks.
Yeah.
Compact and vibration free. This was also
Also don't trust the aircraft instrumentation anymore.
Yes.
What's offload?
You blame them?
Yeah. Because this I still can't figure out, is the fuel industry in volume or in mass?
I think it's
Because
supposed to be
in
in
your car
volume.
you put liters, that's
Yeah,
volume.
volume.
But the pilot is not interested in volume.
No.
He wants mass
Mass.
because that relates to energy and distance, you know.
Yeah.
And then also what he must do with his plane, how much mass he's
Yeah.
losing, and
It's working in pounds.
Yeah, no,
On an
that's
aircraft.
it. That's it. Mass. This is an interesting one. A problem that they deliver with liquid gases, and then they vented the gas, and they got an incorrect balance. It doesn't tie up. And the solution was to take the vapor back to the truck and measure it,
Oh,
because you know you can,
includes
when it
that.
ties up. Otherwise, I think the truck driver stole some or whatever. Petrochemical, this you guys also know, with the contract controllers on your loading bays.
those little flow meters I use on the loading bays, is that also Coriolis?
Yeah.
The small ones? About that size?
In Sasol,
Yeah.
on the loading bays.
No, the
As far as I
contact.
know,
The contact.
those are turbine meters.
That's turbine, yeah.
Turbine,
Sorry,
sorry,
yeah.
It's turbine meters. It's still my job to
That's
change that.
about that size.
The water flow at home, 1 meter.
I'm waiting for industry to change to mass.
Mm.
And I think it will happen.
We're doing good business.
Or PD meters, huh?
Yeah,
It's an oval meter, yeah.
Yeah.
Positive displacement meter.
Yeah.
Now, but the ones I'm talking specifically is on the contracts, where you add your additives.
Yes.
But they're small little meters like that, but that's turbine.
Yeah. I've seen PD meters, I think at the petrol station where you fill your car, they also got PD meters.
Maybe in
Or
news.
turbine meters.
That's positive
Oh,
displacement.
Overseas they have Coriolis meters now in some places. But yeah, I'm all for mass. Here's a case where we replace turbine meters with Coriolis meters. Pulsating flow can also be handled when you have pulsating flow, so the Coriolis meter can cater for that. You know, the flow forward and then a little bit backwards and then forward and a little bit backwards. Gas filling, LPG, again there's a loading carousel. Acids, and again now you need to select your material very carefully. And I've brought some.
Exotic material.
Yeah, you get all sorts of fancy materials. There are limitations with these materials because the temperature coefficient, like we discussed, and then also the vibration, you know. So
And cost that being the
and temperature and so forth. But you have to select the material because there's a whole range of instruments also available now for corrosive applications, all sorts of acids.
Cavitation.
I'm getting. Who said cavitation?
Cavitation.
Yeah, I'm coming to cavitation. That's another headache. Yeah, again, PD meters, Tony. Yeah, they replaced PD meters with Coriolis meters because they had hexene with rubber pellets, and that chokes the PD meters. You know, and then then it's just a tube. Resins, gas. Yeah, here's dispensers. This is overseas. Fueling systems, like a petrol station, where they have cars now, and they do that in mass, all in mass. Food industry, there's a cheese, and they measure the viscosity of the cheese manufacturing. This is an interesting one, and this is a picture that I took. This is Lonman at Rustenburg. And that's platinum slurry going through there.
Okay.
That is a final product. Now, this is such a critical application. The guys get paid bonuses on those 2 meters. Okay, the density. That's what the refinery produces.
And that's also mass meters.
That's mass meters,
Yes.
but they're not really, they get the mass reading, but they wanted the density accurate. Okay, so they wanted the mass
For the product and for the
for the product.
yeah.
That's the only thing that they could use there was a Coriolis meter. Now it was so critical that they bought 2 and they put them in series.
Yeah.
Okay. So they wanted to know accurately. And then we had a bit
They haven't
of
been to
discussion.
our tank farm with Mr. Joey Singh. You put 3.
You know,
But they are running what about on that slurry? 1.6, 1.7 or whatever.
what meters per second?
No, on the density.
The density. Yeah, it's in
That's
that
about-
order. It's in that order.
And that influences your, and that's why it's vertical also.
That's why it's vertical.
Because of the density and so on. Otherwise you can't really measure
You can measure if it's
a
horizontal.
constant flow.
It's not a problem. I'll tell you why it's in this position. That's to minimize abrasion.
Okay.
Okay, I think I'm going to talk about that right now.
Yeah.
But that was a very interesting one, and it works and it's very well, but not without pain. Okay, and it's installed in this way for a very specific reason, and that's to keep them, to make them last. It's also monitored very well, but so far it's a success story.
How often do they replace them?
Because of the slurry.
Not often enough.
Yeah.
We had a very big argument a couple of years ago with Anglo Platinum, where they bought a Coriolis meter and the thing was worn. They installed it accidentally, not properly. They didn't line it up properly, and so the inlet was worn away. And then there was a big fight. They say it's a rubbish meter and we must take it back and give their money back. And we said, look, you guys didn't install it right, you didn't treat it right. But in the end, we took it back and we gave them the money back. And then they went around and they tried mag meters and it didn't work. And they tried this and it didn't work. And I think about 2-3 years later, they came back to
Crawled
us and
back.
they said, oh, they don't crawl. They don't sassel, they never crawl. They said, we, Mr. Customer, and we want to talk to you. To cut the long story short is that they bought, I don't know how many Coriolis meters, lots of them. Big ones, with 3-inch straight tube on slurry application, and it's now working. It's working fantastically. I was on the plant the other day. But now they're doing it right. And this is what I want to show you. Troubleshooting. I'm getting there. This is just a corrosion. You can see the tube is worn here. Now what happens with this Coriolis meter is the mass of the tube is determined precisely. Because if you vibrate it, and it's filled with water, we need to know exactly how to vibrate. So if you now add a little bit of whatever, oil, and it's now a little bit more, I need to be able to measure the density, the increase in density exactly. Okay. So everything is happy. But if you start putting acid through it, and it starts taking material away, it's getting less. And then I get an error in my density measurement. Now that's what happened with the platinum slurry. That's why we said, okay guys, you want to measure this and you want to measure very accurately platinum slurry, but we need to minimize the abrasion. Therefore install it in this, because if you put it like that, gravity grinds it away at the bottom. If you put it like this, it's more even. And then the velocity is very important. If the velocity is too high, the abrasion becomes too high. And then somebody asks, how often do you replace it? Anglo Plat's now at the point where they understand this is a consumable. And again, I'm there with the ship and the oil and the money. If you produce platinum, you can afford to buy a Coriolis meter. Not every year, but they're prepared to replace them every second year. Okay. There's no other way to measure, but we try and minimize it by installing it correctly, by dropping the velocity, and
Selecting the right materials for the tube.
the right material for the tube, and I'll show you a little other tubes that we also do. Then abrasion is of course the other one that takes away material. And what do we do with this? Velocity I spoke about, that's a problem, and you can see the red areas here is where you typically get the high velocity, and that's where you also get the wear on the meter. Then another one is coating, and I'm sure you guys also have applications where you can get coating, and coating is now the counter. Now you're adding mass to the tube. So how do we know this? Okay, we'll get to that now. Solid contents, what they say, if you have something mixed, if you have two fluids, it should be homogeneous. If you let it stand and it
Settles out.
in a minute, then it's actually not suitable. I just want to go back to the slide,
Vulnerability.
what I wanted to show you. Corrosion rate of 0.05 millimeter a year. That's one thing that we're looking at for acids and stuff. Okay, typically another problem that you get is if you have particles in a liquid and you install your Coriolis meter right after a bend, the particles will tend to go to the outside, and then what you get is the one tube is more loaded with particles in the other, and they go out of balance and you get an error. Any ideas how to fix this problem?
Further from the
Yeah. Turn the meter like that, two tubes, and you get a more even distribution, and also install it further away from the bed. We always say that the Coriolis meter you can install straight after a bed, but I mean there are other factors as well. You know. If it's just clean fuel or whatever, it's not a problem.
If you can't avoid it, do it that way, but please,
That's it.
try and give us some distance.
That's it. Viscous fluids, you normally get air trapped in it. Oil, or if you think of honey, you typically get air bubbles in that. And that causes a problem, air bubbles. And then of course non-Newtonian fluids are also a problem when you want to measure viscosity. Newtonian fluids, see somebody frowning? What is Newtonian fluids and non-Newtonian fluids? Newtonian fluids is fluids behaving the same viscosity, doesn't matter what you do to it, if you put stress on it or not.
It's like tomato sauce.
Tomato sauce, you shake it and then it runs.
Yeah. You leave it for a while, then it.
So what's happening is that's pseudoplastic. If you shake it, if you stress on it, then the viscosity goes down. You get also the inverse dilatant, where when you put stress on it, the viscosity goes up. And I think starch in water is that very good example. Yeah. Air bubbles. So what happens with the air bubble? You can see this is the tube now oscillated, and the air bubble sitting there. You don't really know what the air bubble is doing. It's going this way or that way, and it will definitely influence your reading. So some people go and they filter it and that type of thing. But what we say is, if you have air bubbles, try and get rid of it. The law says if you sell something, cassette transfer, you must have an air eliminator. That's one way to get rid of it. Another way to get rid of it, we'll see that now. Air bubbles is the same story. If you have it like that, air bubbles can go into the one tube. We try to distribute it. There was a big discussion which is better, a single tube or a dual tube, because you'd think it's better in a single tube, but in fact they found that it's if you have a dual tube, handles air bubbles better, because this area here is bigger than two small areas. Another thing somebody mentioned, cavitation. So what happens in a Coriolis meter is you get a pressure drop across the meter. I think everybody understands that. And as you get a pressure drop and you have air bubbles, the air bubbles is bigger at the outlet. And if this is in an extreme case, then you get cavitation. So what we do is we put orifice plate here or a valve to create back pressure to minimize that.
And then destroy the orifice instead of the
Yeah, the orifice is.
Coming back to that, and if you go back to the crude oil that's been pumped out ship,
Yes.
there they put two
Coriolis.
in the same line. Because of the diameter loss you get, I mean, you can pump an 8-inch or a 12-inch pipe or whatever and so on, and that's your volume flow or your mass flow. But now you're sitting with this meters, reduce it to, say, from a 12-inch to a 10-inch or whatever. So now you put two to prevent that, or what? Why is there two then?
If you have a 10-inch line.
Yeah.
You can get a 10-inch Coriolis, but the two tubes, the diameter of the two tubes counted together is not 10 inches, not the same. It's reduced. So now they put 2 meters, and then first of all you don't get that tremendous pressure loss
And
across
velocity.
it, and you can put more volume through it. And that was the reason for having the 4 tubes. Those 2 tubes, 2 Coriolis meters, was actually before the 4 tube was built. Okay, but that's just to put more, because if you start pushing too much through here, you can get cavitation.
Now, and the same with this orifice and so on, try to get back pressure.
Yeah.
You have to keep in
Drop it
mind
eventually.
the volume flow you don't want to
The
restrict.
Coriolis meter wants some back pressure. The Coriolis meter wants some pressure inside of it,
Yeah,
especially if you operate with gas. It's very important, because what's happening, this tube vibrates, and what's basically doing, it feels the molecules inside. Now, if you start operating hydrogen, which is very light gas, there's so few molecules in it, and if you then have hydrogen at half a bar or whatever, you know, it can't feel it. If you increase the pressure, you get more molecules, and it's
Then
easy
more
for the
dense, yeah.
instrument to measure it. If you don't have an air eliminator, or you can't make a plan, try and increase the pressure, because what you're doing is you're squeezing the bubble, and then the problem is gone. If you, there was a question, so how much gas can we allow? What we've seen, if you do custody transfer, nothing.
Zero.
If you want to measure density, also near zero, because the air bubbles will affect your density reading. If you want to do mass flow, well, it's not so critical. Not too much, but with those two, absolutely zero. Yeah, you can use a gas separator, increase the system pressure, increase the flow rate. The flow rate will also get rid of gas. We'll change the installation point. Also watch out for this, where you can get air bubbles trapped in places like that, and then they accumulate, and the next minute they go through, and then you see on your
Blip.
you see a blip. You don't know what the devil is causing this. Now I'm going to very quickly, where's the first certificate?
You always have. You determine the pace.
This is the last section, I promise. This is a little bit about advanced diagnostics. I've shown you now how Coriolis meters have developed, okay, and are still developing. And the advanced diagnostics is also something that's coming on now to look after these instruments. Especially, like I said, we are entering foreign territory with the mines in South Africa. These devices come from Europe, and Europe don't have mines. So they look at pharmaceuticals and all that. And we are the tough guys in Africa, and we put mine slurry through a Coriolis meter. Everybody's grabbing their heads and saying, what are you doing? You cannot use abrasive material on a Coriolis meter. But what we're doing now is, when we install this meter, like those two that I've shown you in series, we took a thumb print from these meters. So we filled them with water. They're brand new, they installed. Under those conditions, we fill them with water, and we take all the information from them. And I'll show you what information now. And then what we do is, then a year or what later, we go to the plant, clean them out, and fill them with water again, and take another fingerprint. And then we compare, and we can see the wear and tear or whatever happened on the inside. And that gives the guys a good indication of when do they need to replace. Okay. Because if there is wear and tear on this tube, we can determine and we can see, okay, so how much material has been taken away. And from that we can say, okay, now you have a drift and you have an error on your density. So take the meter out, bring it to us, we put it in the calibration rig, and we adjust it accordingly. We set the zero back. Okay. And then we install it again, and then you can have another run. Okay. But you get to a point where now too much material is away, and you have to replace it. And everybody's not happy with that arrangement. So what can affect it? Corrosion, abrasion, coating, solids buildup, gas, and all those sort of things. And this is typically what we get from the device. We can either get it, if you want this advanced diagnostics, you need to order the meter with this. It's a software function. And you can either get it like that, or we can download it with a tool, Field Care. You can get it in an Excel spreadsheet, put it on your computer, and then you can log it and trend it and do whatever you want. And you can see there's the density, the mass flow, and this is the things that we're really interested in. Tube damping and excitation current. This is all the values that we can get from it. This is the values from the fingerprint. And in this case, you can see there was an increase of tube damping over 5 years of 10.4%. And that tells us that there's buildup in the sensor. So what happened is you have a resonance frequency of the tube, and if you have buildup, it will decrease, and the density measurement will go up, so you get a wrong reading. And the tube damping is the power required to excite the coils. You can see that will slowly drift upwards because there's more mass that you have to now move. And this is what we typically see. This is typically a build-up. The tube damping is going up, the resonance frequency is going down, and this is typically what you'll see, a spike when there's like a slug of air, something going through. And we get alarms from this to tell you what's going on there. So this device is now monitored a lot better. The other side is when you have corrosion, the counter will happen, and again here we will see the opposite. Now just to summarize, Coriolis meters, direct mass, the cost is high, accuracy is very good, long-term stability, the amount that you can put through is limited because the tubes are smaller than normally the pipe. Pressure loss is the one thing to consider on Coriolis meters normally. It's a multi-parameter meter. Installation is easy, rangeability is very good, size is also something that you need to consider, and then it's a very safe instrument. Thank you very much. Any questions?
The vibration on the exciting itself, how's that exciting at what frequency you put it in or what?
This is about at 700 hertz,
Yeah.
and there's a coil here.
So it's low.
Yeah. It's in the order of 700 hertz because depending on the size of the tubes, it varies.
Then it goes lower or whatever,
That's
so on the size of
That's it. But it's in that order. For the viscosity that's twisted, it's a little bit higher, so they operate at different frequencies. But it's still high enough not to be affected by your palm vibration.
Yeah, that's the other question. Yeah. Of course, it's so low.
In the earlier days, that was a concern, but now they found it to be totally independent.
But the excitement itself is what's on the.
It's just a coil that's pulling in and releasing, and pulling in and releasing.
So actually, on the tube itself, is there a little coil or a magnet or what?
That's it there. That's a little coil.
And it's been energized by the frequency generator.
That's it.
Also like
And these are the two